Welcome back to the second part of the lecture, and again, this lecture is all about power in AC circuits. So now we will do the math for the power calculation. So we need to get an expression for the power as a function of time, and we need to do this mathematically. So we know that the power as function of time equal to the voltage as function of time multiplied by the current as function of time. This is a power in any element, or this is a power in any circuit, and we call this power the instantaneous power. So we call this the instantaneous power, and the instantaneous power is the power as function of time. So the power is a function of time is called the instantaneous power, which is a waveform, and you can get this instantaneous power by multiplying the voltage as function of time by the current as function of time. Now let's assume general AC circuit. So in general AC circuit, the voltage and current will be sine waves. So let's say that the voltage V of t equal to a maximum value V max cos omega t. So this equation is a generic cos wave for the voltage, and let's assume that the current I of t equal I max cos omega t minus an angle phi, and this is the current I of t. And how, by assuming v and t with these two functions, we have a generic AC circuit. So let's see this phi. So phi is called the phase shift. So if phi is 0, in this case you have pure R, because the angle between V and I will be 0. If phi is 90, positive 90, you have pure L, because the angle of the current will be cos omega t minus 90, so the current will be lagging the voltage by 90, so this case is pure L. Or phi can be negative 90, and if phi is negative 90, the current will be I max cos omega t plus 90, so the current will have an angle plus 90 compared to the voltage. So this is the situation for pure C. And we can have an angle between these two here. So we can have an angle between 0 and positive 90, and we call this RL. Or we can have an angle between negative 90 and 0, and we can call this RC. So we call this inductive and we call this capacitive. So the angle phi can be between 0 and positive 90 for RL load, a load that has a mix of R and L. If it is pure R, the angle between V and I will be 0. If it is pure L, the angle between V and I will be positive 90. If it is RL, the angle will be between 0 and positive 90. So we call this RL load, or we give it the term inductive. So inductive means it's not a pure inductance. It's not a pure inductance, but it has an inductive part. It has an inductance. If the angle phi between negative 90 and 0, so your load will be RC. So you have RC load, or we name it capacitive. So in this case, these two functions for V and T, for V of T and I of T, is generic. It can capture any type of load by just adjusting the value of phi. So this is the idea of having this generic case. So we will assume V as V max cos omega t, I as I max cos omega t minus phi, and phi is the phase angle, and this phi can represent R or RL or RC or L or C, which are all the cases that we can encounter in any AC circuits. Also, phi is simply the angle theta of the voltage minus the angle theta of the current. So if we look here, the voltage angle here is 0 minus the current angle here is negative phi. So this will equal to positive phi. So we can define phi as the angle of voltage negative the angle of current. This is the definition of phi. Or we give it the term, as we said, the phase angle. So this is the generic equation for V and I. So we can use this generic equation for V and I to find P of t. So P of t is V of t, I of t. So this will be V max, I max, cos omega t negative phi. This is the equation for P of t. And this equation will give you the power as function of time. This will give you the power as function of time for any element. By adjusting phi, you can get the power as function of time for R or for L or for C or for RL or for RC or for LC, any combination. So this equation is called the instantaneous power. This is the power as function of time. And as you can see, this is a wave form. And let's name this equation as equation number 1. And this equation 1 is a correct equation to show you what is the power at any time t. So this equation is correct equation to give you the power at any time t. What we are going to do is we are trying to put this function into another form so we can visualize it. So if I'm telling you that P of t equal V max I max cos omega t minus phi, can you imagine or can you visualize what is the shape of V of this P of t? Can you tell me how we can sketch it? So what we are going to do is we are trying to put P of t on another form that we can visualize it. We are not doing approximation. We are representing the same exact equation but in a different form, okay? Now let's see how we are going to do this. So we will start from this equation here, which is the equation we had in the previous page. So we start by that the power, the last form we have for the power is P of t equal V max I max cos omega t minus phi. So we know that cos A cos B equal to half multiplied by cos A minus B plus cos A plus B. So we know this formula for the multiplication of two cos functions. So if we apply this here, our A is omega t and our B is omega t minus phi. So we can say that if we apply this rule, A equal to omega t and B equal to omega t minus phi. So we can write down that P of t equal to half V max I max multiplied by cos omega t minus phi is cos phi plus cos, the addition will give us 2 omega t minus phi. And this is the second form we have, and let's name this form as form number 2. Now the question is, can you visualize this equation? Can you imagine how this equation look like? So P of t equal to half V max I max multiplied by cos phi, then you have plus, then you have cos 2 omega t minus phi. So can you tell me what is the shape of this waveform? Can you think about, if we need to sketch this waveform, how this will this waveform look like? So the waveform as function of time is a cos wave, and this cos wave has a frequency of 2 omega. Okay, can you relate this to the previous lecture? Why it is 2 omega the frequency for the power? We said that the power will have double the frequency of the source. So if the source do 1 cycle, your power will do 2 cycles. You will have 2 charge discharge cycles. And this is expected from what we did in the first lecture, that the frequency of the power will be 2 omega, not 1 omega. Cos phi. So what is cos phi? Cos phi is a time function, time dependent function, or cos phi is constant? Yes, cos phi is constant. So phi can be 0, so cos phi is 1, or phi can be 90, so cos phi is 0, or phi can be number between 0 and 90. So at the end, the cos phi is a value. So what we will have here, we will have a cos wave, but this cos wave is shifted by cos phi because it is added to cos phi, and this shift is in y-axis. So if we sketch here, so what we will have, so the datum will be shifted, and we will have a cos wave, and this is P of t, and the frequency of this cos wave, so the frequency here is 2 omega, so it has double the frequency of the source. The value of this shift here, this value here, the datum shift, is this constant value here. So the datum shift here is half V max I max cos phi. And as you can see here from this waveform, that the power here is positive, the power here is positive, the power here is positive, and the power here is negative, the power here is negative. Now if you need to find what is the average of the power, which is the average of the area, so it will be simply this line here. So this is the average. So if you take the average power, it will be this green line. So this green line here is actually the average power. So don't forget that P of t is a waveform, and this is what we call the instantaneous power, and it's function of time. But this P of t has an average. So what is the average of P of t? So we said that the average of the waveform will be the datum shift. So the average of P of t, which we will name it as P capital average, this will equal to half V max I max cos phi. This is from the waveform. Or if we take this function again, so if we take this function again, and you start to take the average of the power, so the average of P of t will equal to, so it will be half V max I max multiplied by the average of cos phi plus the average of cos 2 omega t minus phi. As you can see, the average of a cos wave is 0. If you sketch a cos wave, you will see that the positive equal to the negative, so the positive equal to the negative equal to the positive. So the average of any sinusoidal wave will be 0. Okay, So this average is 0, so the average will be the average of cos phi. And we said that cos phi is constant, so the average of a constant is the constant. So the average of the power p of t will be half v max I max cos phi. Okay? So you can find this from the waveform, or you can find this from the mathematical equation or formula you have. So the power in AC circuit is oscillating, it's changing. But this power has an average, and this average is half V max I max cos phi. So why we care about the average? So if I'm saying I will give you money, okay? So I will give you $100, then I will take 20. Then I will give you $100, then I will take 20. Then I will give you $100, then I will take 20. So on average, I'm giving you 80 each time. So this is what you will care about. You will care about the average. So if you are giving your load energy, then taking the energy, then giving energy, then taking the energy. So what you care about the average. So if your load is like a heater and you are giving it power, you care about what is the average power. If you take the average power multiplied by the time, you will get the energy. So to get the energy, which we care about, because this energy will be converted from electrical to non-electrical. If it is motor, it will be converted to mechanical force. If it is a heater, it will be converted to thermal energy. So this is what we care about, is the energy. So what is the energy? It's the integration of the power with respect to time. But the power is charging, discharging. So we can, instead of doing the integration, we can say, okay, the average is the power multiplied by the time. Which power? P average. So we all care about the average power. This is what we care about. Okay, so this is what you pay for at your home. You pay for kilowatt hour. So what is your kilowatt hour? Is what is your average power multiplied by the time of consumption. So we care about the average. Okay, so here we have two types of power. One is called the instantaneous power, and the other one is called the average power. Okay, so let's write down this important power. P average equal to half V max I max cos phi. And now let's say some notes here. If your phi equals 0, so what you have in this case, you have a resistance. So what will be P average? P average will be half V max I max. So what if phi equal to positive or negative 90, which is the case for inductance or capacitance? What you will P average? So your P average will be half V max I max cos 90 or negative 90. It's a 0. So for inductance or capacitance, you are not consuming any energy on average. Why? We said whatever you will consume, you will return exactly. So the average is 0. So what is the productive element we have is the resistance. Inductance and capacitance are interactive element. It takes energy and returns the same amount of energy. And the average power is 0 for a capacitor or inductor. Now, if I'm asking you, we have a 5 ampere load, 100 volt. What is the power of this load? You will answer directly. The power is VI. Okay, so is this the average power? Yes, this is the average power. No, the average power is not VI. It's half VI. So you need to take V max multiplied by I max and divided by half. How we got this half? Just from the proof. Okay, we did this from the proof. If we calculate P average, it's a half V max I max. So what if we did the following? Okay, we said okay, P average equal to V max divided by root 2, I max divided by root 2 multiplied by cos phi. So we didn't do any change. It's the same exact formula. Sorry. So it's a V max divided by root 2, I max divided by root 2. multiplied by cos phi. We called V max divided by root 2 as VR mass. And we called I max divided by root 2 as IR mass, cos phi. And this will be P average. And this will be the average power of the AC power, which is a time varying power. It is a time varying power with this average. And the unit for this, we will discuss the unit later on. Let's keep it P average. And this is another proof for the usefulness of using the RMS. So this RMS will return us back to what we know about power, that the power is VI. There is no half, okay? So you got rid of the half. So to get P average, it's a VRMS, IRMS, cos phi. That's why in AC circuits, we will move from time domain to frequency domain, and we will use the RMS. So if we use the RMS, we don't have to care about this half. Now, we will proceed by finding another formula for the power, and this is the last formula that we are looking for. So I will take again this circuit here, or this equation here, and I will start from it. So this is the first form, and we will find a third form from this form. So this is form 1, okay, number 1, and we did another form here, form 2, the two forms are representing the exact same equation, but just we did a trigonometric formula which convert the cos function into the addition of the multiplication of two cos function to the addition of two cos functions, and this is equation or form number 2. Okay, now we will start from form number 2. So we will do an expansion for form number 2. So P of t equal to half V max I max cos phi plus, we know that cos A minus B. So we know that cos A minus B is cos A cos B plus sine A sine B. So cos 2 omega t minus phi will be cos 2 omega t cos phi plus sine 2 omega t sine phi. So what we did here, we did an expansion for this part. Then we will rearrange this equation. So we will take cos phi as a common factor, and we will divide, or we will multiply half VMIM in the two parts inside here. So what we have here, so we will have P of t equal half V max I max multiplied by cos phi, and this cos phi multiplied by 1 plus cos 2 omega t plus half V max I max sine phi sine 2 omega t. Or we can write it as RMS values as V RMS I RMS cos phi multiplied by 1 plus cos 2 omega t plus V RMS I RMS sine phi sine 2 omega t. And this is form 3. And again, form 1 and form 2 and form 3 are the exact same equation, but in different representation. No approximations are done here. By the way, I will never ever ask you to do this proof. This is not course about memorizing equations and proofs. Okay, so these proofs for you to understand why, how, okay, not just giving you the final result or definition. Okay, once we finish this, things will click together, so you will understand a lot of the confusing concept. Okay, that's why I keep doing these lengthy proofs. Okay, but I will never ask you to do it. Now let's take this equation here. Now you can see that the power in the circuit as function of time, which is what we have physically in the circuit, this is the real power, this is the physical power. So if you have an AC circuit and you measured the power as function of time, this is what you will get, P of t. As you can see that P of t equal to the addition of two terms. Okay, this is the first term and here is the second term. So the power P of t equal to the addition of two terms. Let's name this term as hello and let's name this term as goodbye. So we have two terms. We have the hello term and we have the goodbye term. And to get P of t, you need to add the hello term to the goodbye term. Now let's take the hello term. So what is the hello term? It's a VRMS, IRMS, cos phi multiplied by 1 plus cos 2 omega t. If you look at the hello term, what you can tell about the hello term? What are the characteristics of the hello term? Is the hello term constant or variable? So the hello term is variable. It's a function of time here. Is it linear function of time or it's a sinusoidal? It's a sinusoidal, it's a cos wave. And it has double the frequency of the source. Now, if we need to sketch the hello term, is this hello term will be a function or constant? It's a function of time, it's a cos function. Where is the datum? Is it the datum at 0 or it's shifted? So the datum is shifted and it is shifted by 1. It is added to 1. So at time 0, if we sketch the hello term versus time, at time 0, cos 0 is 1, 1 plus 1 is 2, so you will start at 2. And at 2 omega t equal 90, you will go to 1, you will go to value 1, and at omega t equal to negative 90, you will go to 0, and you will have a function like this. Okay, and this is 2. Okay, this is hello versus time, and the peak here is 2 V I cos phi, and this V is RMS and this I is RMS. And this datum is shifted around 1 multiplied by VRMS IRMS. So this datum is at VRMS IRMS cos phi. So what you can tell about the hello function, so the hello function is always positive. It's larger than 0 here. It is cos function, has 2 omega frequency, and what is its average? Its average is 0? No. Why? Because you are shifted from the datum. So if you look at this function here, cos 2 omega t has 0 average, so the average will be 1 multiplied by VRMS IRMS cos phi, as we did earlier. So the average of the hello function is VRMS IRMS cos phi, which is the same average we found for P of t. So the hello function has the information about the average of the original function P of t. So to get the average of P of t, you need to get the average of the hello function. And the hello function is always positive. What is the meaning of always positive? This power is always consumed. This hello power is always consumed. So this hello power is always going from the source to the load. That's why this hello power is is productive. It goes from electrical to non-electrical, and then you lose it. So if you have a motor, the hello power is the power that is converted to torque. If you have a heater, the hello power is the power that is converted to thermal energy. So this is the power that is going from electrical and then disappear. Now let's see what is the goodbye function, or the goodbye part. So for the goodbye, it is VRMS, IRMS, sine phi, sine 2 omega t. Now if we need to sketch this function as function of time, so this function is a sine wave with double the frequency, and its peak value is VRMS, IRMS, sine phi. So if I need to sketch the goodbye function, this is what I should sketch. So it's a sine wave, so it starts at 0, then it goes to peak, then to 0, then to peak, then to 0 again. So it's a sine function. The maximum value of this sine function is VRMS, IRMS, sine phi. And its frequency is double the frequency. So this is the this is a goodbye function. As function of time. So as you can see that the goodbye function has double the frequency of the source. But what is the average of this function? So this function has a positive energy and has a negative energy, and as you can see, it's around the datum, so the average is 0. Or if you go to the function here, the function of a sine wave is 0. So the average of the goodbye function, is 0. The goodbye function is sine wave. It's a sine function. The frequency is 2 omega. So the goodbye function is charging, discharging with 0 average. So it's not productive. It's interactive. It's an interaction between the source and the load. Now let's give these two functions a name related to their behavior or their characteristic. So we can name the hello as the active component. Why it's active? Because it's always positive, it's productive, it has an average, and it is converted from electrical to non-electrical. So this is your product. And the goodbye function, or the goodbye portion, this is the portion that is interactive between the source and the load. That's why we can call this as a reactive component. So what is the characteristic of the active component? It's a cos function with double the frequency. It has an average. This average equal to the average of the actual power inside the system. What is the characteristic of the reactive power? It's a power with 0 average. It has no average. And it is a sine wave with double the frequency of the source. And your P of t, your actual power P of t, is the addition of the two components. The hello component and the goodbye component. If you add them, you will get the exact power in the circuit. So what we have physically in the circuit, we don't have active and reactive. We have P of t. We analyze it as two components. One is active and one is reactive. Again, in the circuit, we have P of t, which is the multiplication of V and I. We analyze it, or we think about it in our minds as the addition of two components. One component has some characteristic, that's why we called it active, and the second component has other characteristics, that's why we called it reactive. To get P of t, we need to add the active to the reactive. So let's see. So the active component is V. From here on, I will write VI without writing RMS. Now you know that V and I are RMS. This is the default. So Vi cos phi multiplied by 1 plus cos 2 omega t. The reactive component, and now you know why we named it active and reactive, equal to Vi sine phi sine 2 omega t. If we add the two components, the active and reactive component, we will get P of t. And this is what we have in the circuit. This is the actual power in the AC circuit that we name it the instantaneous power because it's a function of time. So we analyze the instantaneous power or the power in the circuit, we analyze it into two components. Now let's take this value here and let's take this value here. So the first value is Vi cos phi. So this value is the average of the active component. Okay, as we did the proof here that the average of the active component is Vi cos phi, which is the exact same average we found here for the power of t. So we found the average for power of t, as you can see, as the same expression. So this value here is the average also of P of t. So we will give this power the name as average power, or we will name it as active power, and we will give it the name as real power, as we will see later on. So the average power or the active power or the real power, which will give it the symbol P capital, is simply Vi cos phi. Why it is the active component? Because this is what you care about. This is what is producing the energy at the end. If you multiply this power by the time, this is the consumption. This is the energy. This is the productive energy. This is the energy consumed or transferred from electrical to non-electrical. Now let's do the same for the second term here, Vi sine phi. So what is Vi sine phi? If we go back, Vi sine phi is the peak of this component. So Vi sine phi is the maximum of the reactive component. And we said that the reactive component is not useful. It's an interaction. This is an energy going back and forth. That's why we will call this power as the reactive power. Or we will name it as later on imaginary power. And we will give it the symbol Q. So Q is a Vi sine phi. Q, don't forget that Q is maximum power and P is average power. So Q is the maximum value of the power that is being interchanged between the source and the load. Now, if you have P and you have Q, how you go back to P of t? So to go back to P of t, I need to multiply Vi cos phi. I need to multiply Vi cos phi by a cos function, and I need to multiply Vi sine phi by a sine function. Then I need to add them together. So can I say that P of t equal to P plus Q? No, this is not correct. Why? Because I need to multiply this P here, I need to multiply it by 1 plus cos 2 omega t. I need to multiply by a cos function. And this Q here, I need to multiply it by sine function. Now let's say a note here. Now let's add a note here. So if you have a vector and you have an angle theta here, and you projected this vector into the x-axis. So say this vector is x. What is the projection of this vector on the real axis? So the projection here will be x cos theta, and the projection in the y-axis here, which is the imaginary axis, is x sine theta. And between the two axes here, between the real axis and the imaginary axis, is 90 degrees. So if you say I have a real plus imaginary, you put here j, and this j means between the real direction and the imaginary direction you have 90 degrees. This is real and this is imaginary. And if the real axis is cos, the imaginary axis will be sine. Let's apply the same rule here. So we need to add a cos, a value multiplied by cos, or a value in the cos direction, to a value in the sine direction. So between the cos direction and the sine direction, or between the cos wave and the sine wave, cos and sine is time. In phasor, they have 90 degrees between them. So to add P and Q to get the instantaneous power, we need to take P, which is the real power, and we need to take Q with a 90 degree. Why? Because between the sine wave and the cos wave, there is a 90 degree. And this will give us the power in the circuit, which will give it the name S vector. Why vector? Because it's a function. It has magnitude and angle. So P of t is a function, and this function has a magnitude and angle. That's why it's a vector. So, and we call this power as the complex power. And this complex power is the actual power in the circuit. So if you measure the power in the circuit, you will measure the complex power, S vector. And this S vector has a magnitude. And to get the magnitude of real plus imaginary, it will be the square root for P squared plus Q squared. So if you take the square root for this P square and this Q square, you will have cos square phi plus sine square phi, which is 1, and this will give you V multiplied by I. And we call this power as the apparent power. Why this is the apparent power? Because this is the power you have in the circuit. So if you have a circuit which has 20 ampere current and 50 volt, the apparent power is VI. That's why we call it apparent. But this power is a wave. It's a sine wave or a cos wave with double the frequency. Its magnitude is VI, but it has an angle, and it's a cos wave. It's changing with time. Now we defined some different powers. So we defined the instantaneous power. We defined the complex power. We defined the active power. We defined the reactive power. We defined the apparent power. But what we have physically in the system, we have P of t. All of these are names. We are using them to describe the circuit. None of these is something that you can see directly in the circuit. Inside the circuit, there is P of t. Yes, we can measure what is the active components, like you have a force in a 45 degree, and you need to measure its X component. You can measure it, but physically, you have a force which makes 45 degrees. If you say this force has two projections, so if you have a force 10 Newton and it has 45 degrees, you can say it has a component in x-axis and it has a component in y-axis. You do this projections or this analysis so you can analyze the system. But what you have physically, you have a force 10 Newtons with 45 degrees. So in the system, we have P of t. This is what we have, instantaneous power. We think about it into two components. One is active and one reactive. Why? Because the active component, if we calculate it, we can calculate how much power is productive that will be an output. And the reactive component is just power going back and forth between the supply and the source. Now we have an issue here. So what is the issue we have? We have the following issue. P equal VI cos phi. Q equal VI sin phi. Magnitude S equal VI. So P is the average power, which is the average of the active component, which is at the same time is the average of the instantaneous power in the circuit. So the power in the circuit has an average P. Q is the maximum of the reactive component. So this is the maximum of the power that being going back and forth between the load and the source. S, or the apparent power, is the power that will appear in the circuit. So when you go to the circuit and you need to look what is the power in this circuit, just multiply V and I. The problem here in the units. So what is the unit for P? So the unit for P is volt ampere, because it's a VI cos phi. Cos phi is scalar, no unit. V is volt, I is ampere, so it's a volt ampere. What is the unit for Q? It's a volt ampere. What is the unit for S? It's a volt ampere. So if I'm telling you I have a load and this load is 50 volt ampere, so you will ask me which volt ampere? Is it the volt ampere for P, or is it the volt ampere for Q, or is it the volt ampere for magnitude S? And instead of going through this confusion, they named the volt ampere for P as what? And they named the volt ampere for Q as volt ampere reactive. And they kept this volt ampere. So whenever we say we have a load with 50 watt, now watt is the unit for active component. So this is the average power. So how you get the energy? Multiply this average power by time. And this is what they do at the meter you have at your home. The measurement is kWh, because this is the active component. So they will charge you for the productive power you consume, not the power going back and forth between you and the utility. For Q, if I say I have a load and this load is 10 var, so now you know that var is a unit for reactive power. So this is the maximum of the power going back and forth between the supply and the load. But what is the power that you will see in the circuit? What is the apparent power? It's VI. Okay, you will not see P only or Q only. You will see S. And the apparent power is simply volt multiplied by ampere. And the unit is volt ampere. So which unit we should use in sizing and in designing in our systems is volt ampere. So when you buy a transformer, when you buy a generator, when you buy any equipment, any piece of equipment, it will be rated, it will be specified in S, in volt ampere. This is the physical power. But P and Q, this is analysis. We use this analysis to see from this volt ampere how much is active and how much is reactive, for us to understand what is going on or to calculate. So if you have a motor and this motor takes 100 volt ampere, can you calculate the torque? No. Why? Because I don't know from this 100 volt ampere how much are productive. To calculate how much is productive that will be converted to mechanical or will be active, I need to calculate the average component. I need to calculate what is the watt power of this motor. And we will see later on that they will define a factor called the power factor, so you can calculate from the apparent power how much are productive. So I hope you understand up to this point what is the meaning of the different component of the power. What is active, what is reactive, and what is apparent. So I don't want to make the lecture so long, so I will stop the lecture here and we will continue next week. This week, as you can see, we didn't do any numerical problems, so I'm not going to do any live examples, but I will be available during the lecture for any help you need. Okay, thank you.